Did you know that levitation is possible? It's not just science fiction. We now have an explanation for the amazing phenomenon of superconductivity thanks to the work of pioneering scientists in the field. Incredibly, this is caused by a supercurrent with zero resistance. But what causes this phenomenon? To see this, we will have to go deeper. Matter is made of atoms. The atom is made of protons and neutrons in the nucleus, along with electrons, which are negatively charged. The flow of electrons through a material is what causes a current. Resistance is the opposition to the flow of electrons. Let's see what causes a resistance. Imagine electrons flowing through a solid, like a metal. This is a crystal lattice made of positive ions. The atoms are constantly vibrating. When an electron flows, it frequently bounces off the atoms in the lattice, slowing it down. The net sum of many electrons bouncing around impedes the flow of electrons, causing resistance. This is known as the Drude model. The Drude model has had great success in predicting the temperature dependence of resistance. When the temperature goes up, electrons have more energy and more collisions, which increases the resistance. What was strange though was what happened at low temperatures. When some materials were cooled below a critical temperature, Tc, the resistance dropped to zero. Not a gradual decrease, but a steep drop to zero. Three physicists, John Bardeen, Leon Cooper, and John Schrieffer, found a way to explain this, winning the 1972 Nobel Prize in Physics. Let's go over their ideas, known as BCS theory. An electron in a lattice affects the shape of the lattice itself. Since opposite charges attract, the lattice is distorted towards the electron. Here's another way to look at it. Imagine, an electron creates a positive distortion in the lattice. This distortion then attracts another electron towards it, in spite of their Coulombic repulsion. In effect, the two electrons pair up, forming a Cooper pair. Cooper pairs can travel smoothly through the lattice. Unlike electrons, they don't bounce off the lattice. Aha! Zero resistance! In fact, this explanation is simplified. The crystal distortion can persist over long distances as the electron is moving. Cooper pairs actually aren't right next to each other. In aluminum, the average radius of a Cooper pair is 800 million times the radius of a single electron. Now back to levitation. Every magnet creates a magnetic field which will penetrate a regular conductor. But don't forget, every current creates a magnetic field too, including our supercurrent. This supercurrent, therefore, will create a permanent magnetic field that cancels out the magnetic field of the magnet right next to it. This phenomenon, the expulsion of magnetic fields by a superconductor, is known as the Meissner effect. Since both magnetic fields repel each other, the magnet will levitate. Magic! So what use do superconductors actually have? Superconducting wire can be used to create extremely powerful magnets. These are used in MRI machines, as well as particle accelerators like the Large Hadron Collider. Liquid helium or nitrogen, however, must be used as a coolant. Superconducting cables could also be used to efficiently transmit lots of power with a small footprint. And remember, BCS theory does not describe everything. High-temperature superconductors have been discovered, which defy all expectations of this theory. Their mechanism is not well understood yet, but scientists have been exploring their properties and complex structures. Finally, the 2016 Nobel Prize in Physics was awarded partly for showing how superconductivity could occur in two-dimensional systems using paired vortices. There is still a lot to learn. This is Ashwin Ramaswamy. Thank you.